So last session we saw group by key. Also we started with pair RDD. So in pair RDD we saw like every time we apply a transformation to an existing RDD to convert it to a RDD of key value pairs, then we call it as pair RDD, right? When we call it as pair RDD, then we call it as a pair RDD, and we saw like the first aggregation, that is group by key, right? We first called group by key, and group by key basically what it does, it just finds out all this it basically finds out the list of values associated with that key. Then we saw a couple of examples, like then we basically applied the distinct operation and set operation to get the distinct type of transactions each person is doing. And post that we checked like whether a person is using that card to make movie ticket purchase and all. So today's part is basically we'll start with the reduce by key function. So what reduce by key does, it's basically reduce by key function basically used to apply aggregations on different keys, right? So as the name suggests, reduce means reduce the data set size. So how to reduce the data set size? By dropping the records? No, rather basically applying the aggregations. So here you can see like transaction RDD.map partitions with index. So we are basically removing the header, and then we are splitting it through tilde, then lambda record of 0, float of record of 1. So record of 0 is nothing but the account number, and record of 1 is nothing but the amount that's available as string, so we convert it to float, right? And now we have a RDD of key value pairs. Key is the account number and value is the transaction amount, and then we try to find out the sum of transactions. Okay, then we try to find out the sum of transactions. So sum of transactions is like this only. So you can see the sum of transaction is lambda amount 1 amount 2 colon amount 1 plus amount. So that's how basically you can find out the total aggregated sum of transactions. Then so that's basically so if you remember last time we discussed about the reduce and reduce by key function. So if you remember like the description of that function, let me walk you through. Reduce by key function. So you can see what it is saying, merge the values of each key using an associative and commutative reduce function. Okay, so this will also perform the merging locally. So that's basically what reduce by key function does. This will perform the merging locally on each mapper before sending the result to a reducer, similar to a combiner in MapReduce. Okay, let's not go into MapReduce in Hadoop. Yeah, I'll come to that. So I'll come to that. So basically, reduce by key function, basically the whole logic is basically it will merge the values associated with each key. Okay, so it merges the values, it applies a reduce function. Reduce functions are all aggregate functions. So it will basically apply aggregate functions per key. So what is the significance of this associative and commutative? That's the key part of MapReduce framework. Okay, that's the key part of the MapReduce framework. So let me quickly walk you through. So what does that mean? So it's saying the functions are associative and commutative. Okay, both reduce action and reduced by key transformation, both are basically using an associative and commutative reduce function. So associative and commutative reduced function. So let's take the example. Let's take the example. Say you want to apply the sum operations. Okay. So what do you mean by commutative and associative? You remember, right? In school time, like in 6th standard, we have this concept like a plus b. What I have like reduced function and reduced by key function, both are taking a binary associative and commutative function. So binary means it's always getting applied on two parameters, right? It's always getting applied on two parameters. So it's always getting applied on two parameters. That is basically, so you can say using a binary associative and commutative function. And you know, like binary means like associative and commutative means like a plus b is equal to b plus a. So this is what we call it as basically binary operations. Okay, any binary operation, if you change the sequence, you'll get the same result. Then we call it as commutative, and then a plus b plus c is equal to a plus b plus c. Okay, that's associative. Like if you change the sequence of the order of the elements, so that will also give the same result. So for addition, it is fine. But for what about the average? So take the example, say number 3. So for the same sum operation, if you take like say 3 plus 5 is equal to 5 plus 3, that means like 3 plus 5 is 8, 8 equal to 8, right? So similarly for associative function, so you can say 3 plus 5 plus 7 is equal to 3 plus 5 plus 7. Okay, so that means is equal to 3 plus 5 is 8, 8 plus 7 is equal to 3 plus 5 plus 7 is 12, right? So implies 8 plus 7 is 15 is equal to 15. Okay, that means some summation operation is both commutative and associative. What about average function? So is it like suppose average of a comma b is equal to average of b comma a? Little boring discussion, but just I just want to make sure everybody is aware of this. And average of a comma b comma c is equal to average of a comma average of b comma c. Okay, so if you take the example, say for like same example 3 5, so you have average of 3 comma 5 is equal to average of 5 comma 3. That means average of 3 and 5 is how much? So what is the formula for average? So 3 plus 5 divided by 2. There are two numbers, right? So 3 plus 5 is 8, 8 divided by 2 is 4, is equal to average of 5 and 3. Same, 5 plus 3 is 8, 8 divided by 2 is 4, right? And what about the associative property? Average of average of 3 comma 5 comma 7 is equal to average of 3 comma average of 5 comma 7, right? So if you take this example, so what happens, like average of 3 and 5 is 3 plus 5 is 8, 8 divided by 2 is 4 comma 7 is equal to average of 3 comma average of 5 and 7. 5 and 7 is 12 divided by 2 is 6, right? So implies average of 4 and 7 is how much? 11 by 2, that is 5.5 is equal to average of 3 and 6. 6 plus 3 is 9, 9 divided by 2 is 4.5. So yeah, these are not equal, right? So that means your average function, if you pass inside those functions, the result what you will get is incorrect. You may get 4.5 or 5.5, but both of them are incorrect. What is the actual? The answer is actually the average of these three numbers. These three numbers is how much? So 3 plus 5 is 8. 8 plus 7 is 15. 15 divided by 3 is 5. The actual answer is 5, but if you are solving that using either reduce function or reduce by key function, you may get 5.5 or 4.5, which in both the cases these are incorrect. Okay, that's the concept we need to understand. So what's the so a little bit of theory back on this is basically you can think in this way. So any distributed computation or MapReduce framework is based on this concept. Okay, so any program or any problem which can be broken into multiple independent smaller problems, those only you can solve it using MapReduce. Okay, so any function like which can be broken into smaller tasks, and you try to connect the dots. There also in Spark also you have discussed like you have in Spark also you have discussed like the smallest unit of execution is tasks, and these tasks are getting executed by different executors in bits and pieces in parallel in round robin fashion, isn't it? So take the example of this. Suppose you're taking the example of this average in associative manner. That means what you're doing, you are first calculating average of two numbers, then you are taking the result and calculating the average of that result and the third number, then that result and fourth number, then that result and fifth number. Like that, you keep on calculating incrementally. You will calculate the result, isn't it? So that's basically how this reduce function and reduce by key function works. So what if you can't solve it incrementally? So those kind of problems you shouldn't solve using MapReduce function or any distributed computation. You're getting my point. Any algorithm you think of, okay, and you want to solve it, it's a bigger problem. So you want to calculate the sum of a billion numbers. So you can't solve it using normal Python, Java, and all. It's very difficult because billion integers means billion times 4. Means each integer is of 4 bytes. So that means it's TBs of memory required to store that element, store that huge list of integers to take the sum. Okay, even small sum operations you cannot solve it using standalone computation if you have really enormous amount of data. Okay, so but is it like you can solve it incrementally? Means you can sum up two numbers, then another two numbers, then another two numbers, like that. Then you should think of solving it using MapReduce framework or distributed computation framework. Okay, but if you're not able to, then you shouldn't try. For average, you saw like average function cannot be broken into this way. Average function cannot be broken into smaller pieces, so you shouldn't try to solve it in this way. Okay, average function you shouldn't try to solve average function in this way. So that's why the average function you shouldn't solve it in this way, because it cannot be broken into smaller independent operations. Then the question is basically, then do you have a lot of limitations in MapReduce framework? Important question, right? So we are saying like average function, we can't break it into multiple pieces, independent pieces. If you're doing that, then we are getting incorrect result. Then how to solve it using MapReduce framework? Okay, so so basically that's basically the thing. So what we are trying to say. So this is so that means like then the question is how to solve it. Okay, so if average is a basic function, we cannot solve it using MapReduce, then it's very difficult. Means what's the scope of this framework? So the answer is basically, so we have to think a distributed version of the same logic. Okay, if you have certain algorithm, certain use case or hypothesis in your mind, and you saw like you are not able to break it into multiple smaller pieces. If you're not able to break it into smaller pieces, then what you have to do, you have to find out a way, or you have to change the logic of that algorithm to solve it in a distributed manner. Okay, you have to think of a way to solve it in a distributed manner. Okay, you have to solve it in bits and pieces. Okay, so that means like instead of calculating average in this way by the logic of what we just discussed now, so a plus b divided by 2, that means like sum of numbers upon count of numbers. So you have to find out a different way to solve it. Okay, maybe instead of like calculating average at each step, so we will be calculating the sum of the numbers and count of the numbers. Okay, again take that results and again use that with the third number. Like that, incrementally you keep on calculating the sum and count, and then finally you just calculate the ratio or the division between them. Okay, so that's why you are seeing like in every other distributed computation framework, so they do have a machine learning framework, but the way they basically come up with different functions in every version release. They don't come up with all machine learning algorithm in one shot, because there are various machine learning algorithms or data science algorithms which are basically which are not basically the logic is already implemented in normal Python. Logic is already implemented in Python or programming language and all. These are all standalone. But if it cannot be solved or it is not associative and commutative, they have to re-implement that in Spark. Okay, that's why it takes a lot of time. Okay, any problem, any algorithm you have used, any regression problems, any classification problems you have solved it in the past using Python, scikit-learn, or R programming. So if Spark is trying to replicate the same solution, it will take time for them. So that's why you still see like there are not all these functions available in Spark machine learning. Okay, it's optional for everybody. Just but have an idea on this. So every algorithm which is not associative and commutative, you have to think up and you have to re-implement that in a associative and commutative manner. Okay, so that's why like we are saying like everything can be solved in distributed manner, provided you should be having that logic how to break it into multiple smaller pieces and then collate the values. Okay, so that's basically about the reduce function and reduce by key function. You should always try this associative and commutative function. Okay, otherwise you may get a different result altogether. Oh, where it is. Okay, so that's basically the thing I just wanted to highlight. So here, yeah. So here basically what we are trying to do. So reduce by key function basically gives you the sum of transaction amount for each customer ID. Okay, for each customer ID, it just gives you the sum of transactions. Okay, then another function called aggregate by key. Okay, and so another variant of the same reduce function is called aggregate by key. So what if you think, one second, if you think logically like how things happen in the backend for reduce by key function. So let me see if I can find some good image to depict that. Oh God, what is this Bing and all? Can you please use Google? Why are you using Yahoo search engine? Okay, so yeah, I think I can get some result. So you can think in this way. So, so you can think in this way, like try to understand like how things happen in the backend for reduce by key function. Okay, so suppose you read the data as 3 partitions. Okay, so you have full bunch of key value pairs, say customer ID and transaction amount, and you have you just read the data as 3 partitions. So in the description, what it says, so it calculates the aggregates first locally. So in each and every partition, it will calculate the aggregates locally, like in the same machine for the same partition, it will calculate locally. Say A is appearing once, B is appearing once. So the sum of amount for A and B are both 1 and 1. Okay, that's A1 and B1. In the second partition,
You can see A is appearing twice, like customer ID A is appearing twice, customer ID B is appearing twice. So the aggregated value is A comma 2 and B comma 2. For basically this third partition, you can see customer ID A is appearing thrice, customer ID B is appearing thrice. So what is happening? So the aggregated value for A is basically 3 and aggregated value for B is also 3. So in the first iteration, so in the backend, when reduced by key is basically calculated, so it first calculates the aggregate values at the key level, okay, at the customer ID level. Okay, so it calculated the customer ID level aggregates, and data shuffling happens. These arrows, what it shows, no? So two arrows. One is inside the partition. Second one is across partitions. So this is called shuffling of the data. SHUFFLE, shuffle. So the data shuffling happens across multiple partitions to basically collocate all these intermediate results shared by the common key. Okay, so you can see A is appearing here with A. So now think about only the result part: A1 B1, A2 B2, A3 B3. So basically it will try to bring all intermediate key value pairs having same key into a common partition. It will form a new partition by taking all results where key is 1. Key is basically A. Okay, so there are 3 partitions. Okay, so it found like say three intermediate key value pair, A1, A2, A3, and it forms a new partition. And then again it takes basically the second the second key, that is B. So B1, B2, B3. So after shuffling of the data, it forms new two partitions, and these two partitions are having the results having similar key: A1, A2, A3, and B1, B2, B3. That's how things happen. Okay, and then the final consideration happened here itself, like locally. Like suppose this is available in machine 1, machine 2, machine 3. After just calculating the local aggregates, it forms new two partitions. Now say it is available in machine 1 and machine 2. So in machine 1, it just calculates the total aggregated value A6. Here also total aggregated value B6, and that's basically the result. If you're calling collect function, it gives you two records, A6 and B6. Okay, that's how basically things get calculated in the backend for reduce by key. Okay, so that's basically the logic of reduce by key function. Got it? Anybody having any query on this? Chandra, Sanjog? All good or nobody following? The same problem you can solve it using aggregate by key function also. Okay, but syntactically it is little different. The things, the input output are same. Okay, you have the same input RDD and same output RDD, but the backend, the way it calculates, it's different. Okay, in the backend, the way it calculates is different. So that's why, so let's see for syntactical, and then we'll see the backend how it happens. So here you just create the same data, credit transaction RDD, and basically you remove the header, and then dot map lambda record colon record dot split, then record, then you are creating a tuple record of 0 comma record of 3 comma float of record of 1. Okay, so this is how basically you are calculating transaction RDD dot map partitions with index. You just remove the header, then dot map. Okay, then dot map, and then dot map, and then what is happening here? So map lambda record dot split, you're splitting it through tilde, then dot map, you're creating a key value pair. Here key is a single element, that's a string, but value is a nested tuple, isn't it? So key is a string, but value is a tuple of string comma float. That is transaction description comma amount. Okay, the last field is transaction description, and the second field is basically the amount. Okay, let's see how the data. Okay, anyway, like we have not put any print statement. So now on that we are trying to apply reduce by key. Just try to visualize. So here each and every key value pair is looking like this. Key is customer ID and value is a tuple containing transaction description comma amount. Okay, then you are saying reduce by key function. Then you are passing the key value. You're passing two values. So what is the data type of this element and this element? Sanjog, Manjunath, what is the data type of category amount 1 and category amount 2? Nobody?
Float.
No. Sorry? Sandeep?
Interior.
No.
I guess it is a tuple.
Tuple, correct. So the data type of category amount is a tuple of string comma float. Why? Because you have a RDD, you have a pair RDD you have created in the previous shell. So this account transaction category RDD is a RDD of key and value pairs, where key is the account number, which is a string, and value is a tuple of transaction description comma amount, that is a tuple of string comma float. So when you are calling reduce function or reduce by key function, it takes the value part only. Okay, these two are the value part of two records. Okay, so the data type is tuple of string comma float. That's how things happen. In reduce by key function, the data type of this attributes are string comma float. Then basically you are creating this way. Then basically you are calculating the, say I'm calculating the maximum value. Just like you calculate some value, similarly max is also an aggregate function. Okay, so we previously saw aggregate function, that is sum. You keep on calculating the sum of amount. Here I'm calculating a different aggregate function called max. Okay, a same customer ID can have multiple transactions, and I'm checking like which transaction is having highest transaction amount. Okay, so for that, what we are doing, we are basically calling the map function. So what we are saying, if category amount 1 is, so you're saying like the if amount part of the first record is greater than amount part of the second record. Record means I refer these parameters. So I'm saying if amount part of the first value is greater than the amount part of the second value, then return this amount part of the first, else return the amount part of second. This is also a syntax in Python. Okay, so in inline also we can define the if expression. Okay, if condition satisfies, then the earlier element. If condition not satisfied, the else part. Okay, so here that means you have the input RDD is a RDD of key value pairs, where key is a string and value is a string comma float. But after calling reduce by key function, looks like you are returning only the amount part. Means you are changing the data type of the value part from string comma float to only float. Okay, which will fail. Okay, in reduce by key function, it doesn't allow you to change the data type of the value part. Okay, just remember, every time you're applying reduce by key function on a pair RDD, you're applying some aggregations on the values. You won't be able to modify the data type of the value part. Okay, if the data type is integer, you should return integer. If data type is a tuple of string comma integer, you should return a tuple of string comma integer. But here you are only extracting the amount part. Okay, that parameter within square bracket 1 means the second element you are extracting, that is the amount part. You're only extracting the amount part, so that's why it's complaining. Okay, it's saying like you cannot apply this kind of transformation, but that's fine. But you can solve it in this way. Just to show you one caveat, in reduce by key function, you won't be able to modify the data type of the value. Okay, here basically we solved it in a different way. Instead of returning the amount part by using the square bracket of 1, so what we did, we just return the value as it is. Okay, in the previous example we did this, right? Category amount of 1, we just extracted the second field, the amount part, but here we just return the entire value as it is. Okay, now after this reduce by key function, you have the result, that is key value pairs. Key is the customer ID and value is the transaction description and amount. Okay, wherever the amount is the highest. Okay, suppose customer has done multiple transactions in electronic store, in gas stations, in parking, and all this. So which transaction is more along with the transaction category or description. So all these things you got as the result of reduce by key. Then what you did, you apply map function to convert the data type of the value part. So here you saw, but I want the value that is what's the maximum transaction. So for that, what I did, I again applied a map transformation, map lambda record colon. I'm creating a tuple that is containing record of 0 and record of 1 of 1. Okay, record of 1 of 1. So that's basically the result. Okay, so if you execute this, you are getting the transaction amount corresponding to, sorry, the highest transaction amount corresponding to each customer ID. Okay, each account number. Okay, so that means one observations, like in reduce by key function, you won't be able to modify the data type of the value part. Okay, but you can solve it using two steps. Like you first calculate the you first apply the aggregation function and later apply another map function, additional map function to get the result. And that's there. Then basically what we are doing, so that is basically the reduce by key function examples. So then how this particular situation has been handled in reduce by in aggregate by key function, that we need to understand. In aggregate by key function also we are doing the same thing, but what it does, it takes two functions. Okay, it takes two functions. Just think in this way. So here you saw you are applying some aggregations at each partition level first and then across partition level, isn't it? You first apply and suppose your objective is to find out the sum. So for each key, so how Spark calculates this? It first calculates the local aggregates at each partition separately, and then the data shuffling happens. Okay, means basically keys associated with the intermediate value fall under a single partition, and then the consolidation happens. There are two type of aggregations happen. Means the same aggregation happens locally across partitions also. Okay, we have a common sum operation. That sum operation is getting applied in the local or the intermediate result calculation and as well as the consolidation. But aggregate by key function has two functions. Okay, it basically takes two functions. One function is used to calculate local aggregates, and for shuffling for global aggregates, it uses a second function. Let's see, like what does that mean? So here you see aggregate by key function. It takes three parameters. First one is the initial value. You are applying some aggregation. So do you want to start with some initial value, or you directly want to start with the actual values? You have customer ID C1 having three records, 100, 200, 300 transaction amount. So you want to sum up in this way, like 100 plus 200, 300, 300 plus 300, 600 in that way, or you want to start with some initial value. Okay, so you want to start with say 0. Okay, 0 plus 100, 100, 100 plus 200, 300, 300 plus 300, 600. Sometimes you may require to start with the initial value. Okay, so for example, you are trying to calculate maximum of transaction amounts. So you have 100, 200, 300. So that means here you have to start with the initial value. So what initial value you have to start with? You want to calculate what is the maximum amount that person has done transactions. So when you are calculating maximum, first time you have to compare with some value, and that value can be a minus infinity. Okay, minus infinity and 100, which is maximum. 100, 100 and 200, which is maximum. 200, 200 and 300, which is maximum. 300. Okay, that's the significance of initial value. You can start with the initial value and then start doing the aggregations. Okay, similarly, you want to calculate the minimum. Okay, 100, 200, 300. First, you start with the initial value, say positive infinity and 100, which is minimum 100. Then 100 and 200, which is minimum 100. Then 100 and 300, which is minimum 100. So in that way, you can keep calculating the aggregates. So the first parameter, the significance of first parameter is the initial value. You want to start with the aggregations for each key, not the entire data set, rather per key. Per key, when it's doing the aggregations, it starts with the initial value, and then some at partition, some across partition. In some at partitions, okay, you can say it takes two parameters. Of course, this aggregation, it should take two parameters. In some across partitions also takes two parameters, but there is a difference. This first parameter, I'm calling it as accumulated value. The first parameter is taking its data type is not the actual data type of the value part. So what is the data type of this particular RDD? It's a tuple of string comma float. Means the value itself is a tuple of string comma float. Means transaction description and amount. isn't it? So here some art partition, this part is a float, but this part is a tuple of string comma float. Why it is like that? Because the initial value what you have started with, the initial values data type is float, system.float info.min. It results into minus infinity. Okay, not minus infinity, rather it's a huge negative float number, decimal number. Okay, so since its data type is float, so sum at partition function takes the first parameter as a float. Getting my point? So since this aggregate by key function takes the first parameter as a float, even though the RDD is having the value part as a tuple of string comma float, so the first parameter is becoming float. This is the first parameter, and the second parameter is the actual data type of the values. Actual data type of the values. So that is there, and then sum across partitions. So means after applying the sum at partition, whatever the result you resulted into. Okay, suppose in this function gives you a chance to change the data type of the value part. Okay, in reduce by key function, it's a straight big no. You can't change the data type of the values. But here, if you want to make any change, you can do that in this particular function. That's why cleverly here only we changed it. We took the initial value that is a float value, and these are the actual key value pairs, string comma float. Here we made a comparison which is maximum. Then we returned that value only. We are not returning the element as it is, rather the amount part only we are returning. So that means after applying the aggregation functions locally in each partitions, your RDD has the elements that is string comma float only, not string comma tuple of string comma float. Because after calculating the aggregations at locally, we converted the data type from tuple of string comma float to only float. Okay, that's basically we did. Now your sum across partition will take the data type, which is the result of the previous function. Here we resulted into float. So these two are float and float. And it's just calculating which one is maximum. Same thing I will repeat. If you are attentively listening, then you can understand it in one shot. But if you are sleepy and all, you have to recap this video again. Okay, it's straightforward. So the comparison, what I tried to make it here. So in reduce by key function and aggregate by key function, both are used to calculate aggregates. The reduce by function has a restriction. You cannot modify the data type of the value part. After applying the aggregations, you should return the exact same type of value. Key part anyway are remaining untouched in both the cases. Key part you can't tamper it. Okay, customer ID C1 means C1, you can't modify it. But the value part you saw, it was transaction description comma amount. So you want to basically convert the value to only the amount part, what's the maximum or minimum amount. Then you can solve it using both reduce by key and aggregate by key function. In reduce by key function, it's a two-step process. As you know, like every time you keep on adding multiple transformations in the backend, more and more number of tasks are getting applied. But yeah, that's not a bad thing. But yeah, and if there is a way we can reduce the number of tasks, we can do that. Okay, don't think like I'm creating new tasks. No, it's a bad program. No, it's not like that. You're still fine. Okay, as for your own convenience only. But just make sure like here, just make sure like what you are trying to do. So if it is possible to reduce the number of tasks, we can always do that. Okay, we can always do that. So now here what we are doing, here we applied the modification. Okay, here we in the reduce by key function, you didn't modify the result, and then later you applied a map function to modify the data type of the value part. But in aggregate by key function, it has a lot of flexibility. You can start your aggregations with the initial value, and you can pass two aggregate functions. One aggregate function will be used to calculate local aggregates, and another aggregate function will be used to calculate the global aggregates. Okay, and while calculating the local aggregates, there itself you can apply the modification to the value type. Means apart from applying the aggregations, if you want to change the data type of the value, or you have to transform the value from one format to another format, that you can do at this function itself. Okay, that's the whole logic. Let me just see like if I can find out some good image for you. Not this one. Let's see this one. This is the example. So here, if you just look at it carefully, you should thank this guy. He has created a good image. So you can see Thomas physics, 93, Joseph physics, 74, like that. Key is the student name, value is a tuple of score, subject, score. Okay, so we are calling sum at partition. Technically, it is called sequence operation. Okay, or so we are going to calculate the maximum scores. So here only what you did, for every student you found out the maximum score. Okay, so and you saw like here we ignored the score part. Okay, here you can apply the aggregates. Along with that, you can transform the value part from one format to another format. We applied the aggregates, like we found out the maximum score, and then we converted the value part from string comma integer to only integer. For all these three partitions, you did the same thing. Okay, for all these partitions, you did the same thing. And then some across partition is called combine operation or combiner operation. Okay, so here basically what you're doing, you're basically calculating the total, you're collecting the values associated with each key. Okay, Jacqueline is having 86, 83, 75. So it collected all values from all these three partitions. Okay, and then it basically for Jimmy, like it calculated the intermediate aggregates from all these three partitions, 74, 97, 80. Okay, like that it just extracted the or collated the intermediate results for each and every key separately. Okay, in two different partitions. You can say why two partitions, why not one, or why not three? So this is completely dynamic. Okay, so we'll see like in both reduce by key, group by key, aggregate by key function, it has a separate parameter that says like you want to keep the number of partitions same, or you want Spark to decide the number of partitions. That's a Boolean flag. If you say keep the partitions, so after applying the aggregate by key, you will again get same number of partitions. But if you say no, means if you say false, then Spark will decide the number of partitions. Okay, so most of the time we do allow Spark to decide the number of partitions, because there is no point in creating same number of partitions, because you have say 5,000 partitions. After applying the aggregations, the volume of data will be drastically reduced, isn't it? Suppose each student has thousands of records, these will be merged as a single record only. So the volume of data will be reduced like 100 or 1,000, which is the nature of the data. So let Spark decide. So it just decided two partitions. Here you see Jacqueline, Jimmy, Joseph having these records, and Corey, Joan, Thomas, Tina are having these intermediate key value pairs. And then it calculates the total aggregates. Okay, so Jacqueline has 86, Jimmy has 97, Joseph has 91. Like that, this final aggregation happens. Getting a point? So that's basically how things happen in the backend for aggregate by key. First time it has values as tuple of string comma integer. So it calculates the aggregates and end up getting only integers. Okay, for all these three partitions. And then when the shuffling happens, it calculates in a different way. Here your records are like this: okay, customer ID and the list of values, or student list of all scores, and then it collates the values, then it finds the final aggregates. Okay, that's how things happen in the backend for aggregate by key. So very common question. If a person is getting deeper into RDD, for sure he'll be asking these questions. What's the difference between group by key, reduce by key, and aggregate by key? Which one you think is better? Okay, all these questions comes. So anybody having any queries before going to the comparison?
So Siddharth, which is better? Up to you.
What do you think? Which is better?
I mean, among three, what your answer will be for which is better?
That's what. No, why you are putting me in trouble? There is nothing better, nothing worse. These are end of the day, there is no emotions. These are all APIs written. What's your requirement basis that you have to use the right function. If you have requirement X, but you are implementing using Y approach, then only this comparison will come. Otherwise, each and every function has equal importance, and it has written with a different intent, isn't it? So, for example, before that, anybody having any other queries like on this, like in terms of like the backend logic or any other confusion on this aggregate
So
by
Siddharth,
yeah.
yeah, in real time, like even in data frames also we use like more time, like comparison of reduce by or aggregate.
Not more time, you always use data frames only.
Okay.
We will never get a chance to use this RDD functions. But yeah, conceptually, do you have any confusion on this? Like if you're individually discussing about group by key, reduce by key, and aggregate by key. So is it clear, or you are having some confusion? Forget about the comparison. Comparison will come later. Okay. So if you're clear, so let's discuss about the comparison. So let's try to connect the dots. In group by key, what we did, we just calculated or we just collected the list of values associated with each key. That's basically group by key, isn't it? We just collected the list of values with each key. And on top of that, you can do some further analysis. You want to find out the distinct list of transactions or distinct. So you have a bank transaction data. You want to find out debit, credit. The person is only depositing or he's also withdrawing. Suppose you're checking the money laundering case. So if a person is keep on depositing for quite a long time, that means he's collecting funds from different parts, and then he may use that in one shot. So that can be possible. So in that way, you are just calculating the list of or the type of the categories of transactions, only debit or credit or both. Okay, so you are trying to find out the list of customer who has only crediting amount. So those are risky customers kind of. Okay, so those kind of analysis you can do. Or a person is coming to your supermarket, you are a owner of a supermarket, then or a store, and people visit to your shop, and you want to calculate like customers are spending money on which categories products. Okay, so if you see like all people are basically, you have added some you have a space issue, you have taken a 2-story building and you want to add a new category of products, and you see like from your existing 10 categories of products, one category is undersold, like hardly a person is using, like out of your 1,000 customers, only 1 or 2 customers are purchasing those products. Then you can safely think of like replacing that category with a new category what's in your mind. Because those kind of analysis you can do it using group by key. You can find out like each customer and the list of transaction categories they're doing. Are they purchasing apparels? They're purchasing groceries. They're basically purchasing puja needs. They're basically purchasing snacks. So what are the different categories of product they're purchasing? So basis that you can do multiple analysis. And reduce by key function when you want to apply some aggregations. Okay, you want to basically apply some aggregations basis certain key, you can do that using reduce by key. And same with aggregate by key function also, with additional flexibility to apply to start with the initial value, and also the aggregations, one type of function at a partition level and one type of operations at a across partition level. So if you try to calculate the aggregates using group by key, you will get bad performance. Obviously, because it's not meant for that. People compare it, but it's not actually apple to apple comparison. These are completely different stuffs. Somebody will say, I want to calculate the aggregates using group by key. So why will calculate the aggregates using group by key? Because it's not meant for that. But still you can calculate. You can collect the, suppose you want to find out the sum of transactions. You will call group by key and you will get the list of transaction amounts associated with each key. And then you will apply again another map operation to find out the sum of the values in the value part, right? So that also you can use to calculate the aggregates. But don't you think like it will be a heavyweight process? So in reduce by key, it's calculating the aggregates locally, isn't it? It calculates the aggregates locally. It calculates the aggregates locally, and these intermediate values are only shuffled across the partitions, isn't it? So in reduce by key, it first calculate the intermediate values, and these intermediate values are shuffled across. Here you have 4 million records. These 4 million records are only reduced to 2 million, and sorry, 4 million records. So A has a million record, B has a million record. This is reduced to only 2 records. Means 4 million, sorry, multiple millions of records are converted to only 2. And these 2 records will be moved across in the next step. Here you have 6 million records converted to 2 million. So you can see 1/3 data reduction happened, and these are moving across different partitions. That's how reduce function happens. But if you use group by key will, what it will do? It will collect A1, B1. Here A11, B11, A111, B111. Like the list, the value will be a list of these values. And that huge records, suppose it's a 6 million record. That means A, 3 million values as a list, B, 3 million values as a list. So that huge list will be shuffled across the partitions, across different nodes. So this will be a huge IO happen, huge input output happens, huge amount of data will be moving across network. So obviously that will be a heavyweight process. You shouldn't solve that using group by key, because group by key's job is that it will just keep collecting the values associated with the key. But here we are keep summing up or keep aggregating the values associated with each key. So these are two different type of functions. So we should solve a given problem basis the function available in the APIs. You want to calculate the list of values, then you use this. Then you use this group by key. If you want to calculate aggregates, then you can use reduce by key, like that. Got it. So that's basically the difference between group by key and reduce by key. And reduce by key and group aggregate by key, you can think in this way. Reduce by key function is a special version of aggregate by key. Aggregate by key function just has two different aggregate functions as parameters and an initial value. Whereas you can say reduce by key function is a special variant of that, where both the sequence operations and combine operations are one and same only. Okay, both the sequence operation and combine operations are both one and same only. Okay, that's basically the reduce by key function. And performance wise, these are one and same only in terms of like flexibility. You want to change modify the value type, you want to start with the initial value, then you can go ahead with aggregate by key. Okay, otherwise if you don't have any requirement, you can directly go ahead with reduce by key function to calculate the aggregates. Okay, that's basically the logic here. Okay, hope that like clarifies the doubts. So anyway, like you can brush up through recording again. It's a very important concern many interviewers ask. Okay, so to understand your conceptual clarity. So then another example for the same aggregate by key function, I think I copy pasted that there. So student ID, subject, and score. This is not a pair RDD. You can see I've created a tuple of 3 elements. So this is not at all a pair RDD. It's just a regular RDD. Then I converted it to a pair RDD here in line number 17. Student colon student of 0, student of 1, 2. Okay, so key is student name and value is subject comma score. Then you are applying aggregate by key function. Initial value you're starting with 0 and you're calculating the maximum score. Okay, so that's basically how you have calculated. Okay, for all these subjects along with the scores. By the way, these are the list of people who got like 200% hike from my training, from some different training batches. So that's why I've given some examples to remember those names. Anyway, so that's basically about your aggregate by key and reduce by key. The next example is map values. Okay, the next example is called map values. So as the name suggests, map the value part only. Normal map function map the entire record. Okay, you are applying some transformation on the entire record, but map values, it's basically applying some transformation only on the value part. Okay, so that means it's applied on the pair RDD, and you can apply some function on each. You can apply some function. You can apply some transformation on the value part only. Okay, that's basically the map values function. So let's see. So here basically you have the same RDD, credit transaction RDD, and then you are saying that RDD dot map partitions with index to remove the field header. Then you are saying map lambda record that split, you split it through tilde. Then dot map lambda record, a record of 0 comma float of record of 1. So you got the transaction amount. Okay, so on that particular RDD you're applying map values, and map values will convert the value part from map. So it will basically convert the value. Let's first see how the data looks like. So you can see this is the key value pair. Key is the account number and value is the amount. And then what you did, you applied map values saying amount colon amount comma 1. That means you converted this value part from 1 comma 23 to a tuple containing 1.23 comma 1. So let's see. This is what the result. Key is the student ID and value is a float comma integer. Then basically what you are saying, you are saying reduce by key function. Okay, then you are calling reduce by key function. Then basically you are calling reduce by key function. In reduce by key function, what you are doing, lambda of amount 1 comma amount 2. So what is the data type of amount 1 and amount 2 here? Sandeep?
Yes, Siddharth. So I think it's going to be 1.23 for the amount one, and
No, here there is a catch. No, when you call reduce by key function, it takes 2 records at a time. Okay, suppose here the key is 1, 2, 3, ABC 789, and here also 1, 2, 3, ABC 789. These 2 records been passed at a time. So their
yeah,
value.
so for that record, it sums up, right? 1.23 plus 2.36.
No, I'm saying like what is the data type of amount 1 and amount 2?
String and flow.
No, you can see it clearly. So the key part is string. Okay, in this RDD, before calling the reduce by key function, I saw the output. It's creating a RDD having key as the integer and value is a tuple of float comma integer. So amount 1 is also a tuple of float comma integer. Amount 2 is also a float of integer float comma integer.
Okay.
Because it takes 2 values at a time for a given key. So for 1, 2, 3, ABC 789, so it will pass amount 1 as 1.23 comma 1, amount 2 as 2.36 comma 1.
Okay.
Okay, so then basically what it did, so then basically you can see like it takes amount 1 comma amount 2, and it calculates the sum of the first part, amount 1 of 0, amount 2 of 0, and also it's summing of the amount 1 of 1 and amount 2 of 1. Okay, it calculates the aggregates. It calculates for every key, it find out the sum of the amount and sum of the counters. Okay, that's the logic of this reduce by key function. So now you can see for each and every customer ID, you are finding out the total sum of transactions and total number of transactions. That was the logic I was implementing. Just listen, yeah, don't. I'm about to like discuss about the fourth or fifth example and this fourth or fifth examples and this reduce by key and all. You're still getting confused with the value part. Just remember, all reduce by key, group by key, and all they all take uh, the value part as the parameters. Okay, because key, as the name suggests, reduce by key means by key means it's always the key part is addressed there. Okay, so it will basically reduce by key means per key it will pass 2 values and aggregate it. Okay, here key is a 987 CBA 321. So for this particular key, how many occurrences of records are there? So basis that it will keep on calculating the aggregates. Okay, so this amount 1 and amount 2 are the values corresponding to this particular key. Again, for a different key, it will do the same thing. It will keep on sending 2 values at a time and calculate the aggregates. Okay, like that. Let me calculate the values in that way. Okay, that's basically how the things happen in the backend. So that's basically what we calculated here. We calculated the total sum of transactions and total count of transactions. Now again, we applied a map values and we said lambda record of 0 divided by record of 1. That means again this record map values is taking the value part. Value part is nothing but a tuple of float comma integer. So it takes the float part divided by the integer part. This is nothing but average. Okay, you calculated average in this way. So that's what I was just trying to highlight. If you directly try to solve the average function using reduce by key function, you will get a wrong result. Okay, if you remember the example we just discussed, like 357, you may either get 4.5 or 5.5. In both the cases, the answer is incorrect because the actual average is 5. So because average function is not associative, so if you solve it using a reduce by key function, you will get a wrong result. Okay, you'll get a wrong result. So for that, you have to solve it. You have to break that problem into a distributed way. Okay, then you should solve it. Okay, and we know like average is nothing but sum of the numbers upon count of numbers. That's why we use map values and reduce by key collectively to find out the sum of values and sum of count of records, and then we are calculating the division between them, and we solve the average problem. Got it? Anybody having any queries? Tausif, Rohit. Anybody having any query?
No, Siddharth.
No, see.
Okay. Cool. So let's go to the next example. Count by key. Count by key is again another action. It basically count the number of occurrences of records per each key. It's not a very tricky function. I'm just showing it. You have RDD having key as the customer ID or account number and value is the amount, and you're calling count by key action. So it returns a dictionary having keys the account number and value is the count of records. This way we can count the number of records per each key also. Okay, that's there. And then joins. Joins, I believe everybody is aware of joins. Okay, let me put it in this way. Let's make it more interesting. So suppose you have table A, sorry, table 1. Having say customer ID, amount, say it's a sales table, and you have table 2, customer ID and name. Okay, so suppose this is having 100 and say 10 records, and this is having 10 records. Okay, so now what is the minimum and maximum number of records you will get? Then you apply inner join. What is the minimum and maximum numbers you will get in inner join? Left outer join, right outer join, and full outer join. Manjunath.
Inner join minimum 1, because if minimum if ID matches, it's
Sorry, if
1.
sorry,
If they have like same ID, it will be minimum 0.
minimum 0. Okay.
Yeah, maximum 10.
Okay, so basically what Manjunath is saying, if you're applying inner join in these two tables, minimum will get 0 number of records. For example, say this is a sales data of Walmart, and this is the customer table of Amazon. Okay, here whole bunch of
Okay, now.
different IDs and here whole bunch of different IDs. So you join them, there is no matching, so 0 number of records. And maximum is saying 10. How it is 10?
So if like all the IDs matches.
All these ID matches. So that means you are saying here also 10 distinct IDs and same 10 distinct IDs here. So 10. Is there any other condition? Anybody having any other answer? Maximum result? Tausif? Chinna? Sai?
Maximum should be 10.
But if like this table is having ID 1 for all 10 records, ID is C1, customer ID C1. And here also all these records are having customer ID C1. How many records you'll get after joining?
20.
Oh, come on. Hard is 20. Think. What is the logic of inner join? It will give you records for every matching result. So
Yes.
when you are taking first record C1, amount say 100. And here in the right hand side table, same C1 is appearing for 10 records. So for the first record, it will get 10 records. For second record, it will again get 10 records. For third record, again 10 records. So it will be kind of a cross product or Cartesian product. It will be 100. Maximum will be 100. Getting a point. So first table is customer ID C100, C100, C100 10 times. And in the right hand side, you have C1 Siddharth, C1 Siddharth, C1 Siddharth. So for every record in the left side table, it will be appending, it will merging it with all these records in the right hand side table. So you will get, yeah.
In such a case, table 2, right? That C1 will be the unique key, right? So that should not be an
I
duplicated.
don't know. I'm using some table. It doesn't have any constraints. It doesn't have any primary key, unique key. Any constraint has been implemented. Because that was not the condition, right? We just said like these are two tables and we are discussing about the minimum number of results and maximum number of results. We are least bothered about the constraints applied. But if this is the question, how to answer it? This is possible, right? If there is no constraint, a table can be having same record repeated. In fact, in interviews, you will see a very common question people ask, like, how do you remove duplicates from a table? Isn't it? Every interviewer asks, like, how do you remove duplicates from a given table? Okay, so this is the case, like C100, C100 10 times, C1 Siddharth 10 times. If you join them, you will get 100 records. What about left join? So now everybody clear about the inner join. Inner join always gives the record based on the matching condition. Okay, you're putting some matching, say you say select A dot star, B dot star from table 1 A, join table B, say table 2 B on A dot ID equal to B dot ID. So you're joining them through the IDs. So there basically it gives the result in this way. It basically matches the IDs and basis that it gives the values. Now, what is the result in case of left join? How many minimum records?
10.
Okay, minimum records 10. Maximum?
100.
Correct. So left join, like it will give you all records from the left hand side table for sure. And there are 10 records, so you'll get minimum 10 records. And sorry, any confusion?
No, sir.
And then maximum same condition. If you have a cross product, same record is repeating across all, so then it's 100. and right join also same 10 comma 100, right? There is no difference. And full outer join,
20.
how it is right, the minimum
No.
100.
minimum 100.
Minimum 10.
Minimum
Yeah.
10.
Maximum 10 is 100.
Okay. That's the result. Okay, many people are having this confusion. That's why I thought like let's discuss this first. Let's see the syntax. So here in RDD, it's not structured data, it's basically a collection. So joins are available only on pair RDDs. On regular RDD, it is not available. If you have RDD of list of values, RDD of tuple of 10 fields, RDD of integers, so you can't join them directly. Joins only happens on pair RDDs. Okay, it's RDD of key value pairs, and the joining happens through the key part only. Okay, you have one RDD having customer ID and amount, another RDD is having customer ID and name. So when you are joining them, so the join happens versus the key part. The join happens with the key part always. That's why there is no, so the function what we are using, it even doesn't have a joining condition. This is the customer transaction data. This is the customer's name. This data, can you upload it, please? Customer name. Okay, so now you're basically trying to apply join. So from this customer data set, you saw the header is account number and name. So you remove the header and converted it to a pair RDD having key value pair, customer ID and customer name. And then you are basically applying join. You can see join functions take only a RDD, no joining condition and all, because by default joins happens on the key part. Okay. Then you are basically saying this is the result. Okay. And also observe the pattern of the result. Each record, like every operation on pair RDD always results a pair RDD. It also a key value pair. If you observe it carefully, each record is a key value pair. Key is the customer ID, obviously, because basis that join happens, and value is a tuple now. We don't have either of these input RDD having value type is tuple, but after joining the value types become tuple. Why? Because this tuple is having first element as the value part of the first RDD and second element as the value part of the second RDD. Okay, for every account number you get value is of type tuple having key as the amount and value is the customer name. Okay, that's basically the thing. That's basically how things happen. Total so basically from this joined RDD we're trying to find out. So this is basically how joins happen. Okay, the result will always come as a tuple of values. First part is the value from the first RDD, second part is the value from the second RDD. Okay, like this. outer join and all these things you can just verify. You just created the same data. Like I think the first RDD is having, both are having 4 records, but only 3 are matching. 1 are basically different. So basically that you can figure it out. So now there is a concept called, any confusion on joins? Anybody having? Just it accumulates some values, right? So accumulators and broadcast variables, these are 2 additional concepts here in RDD. So what that does are basically accumulators and broadcast variables. So whenever you are trying to implement some counter, okay, you want to implement some counter, so that is basically done through this what you call accumulator. Okay, so let's see like what do we mean by counters and all. So this is the same log RDD, and we created this is the same logs RDD, and we created a variable, say it's a counter error log lines. We started with the count 0. Then inside this RDD, we are calling for each. For each is an action lambda log. So we are saying error log lines +1 if error in the log. Okay, so in this particular variable, in this log, we are converting into uppercase. Okay, and then you are checking like if error is a substring available there. Here you can see info error. This strings are there. You're basically trying to count the number of error logs. Okay, so you say if error in this log, then increment the counter, else just keep the counter as it is. And after this, you are basically saying print this. So what happened? You're getting only 0, whereas actually how many errors? 1, 2, 3, 4, 5, 6, 7, 8. 8 errors are there, but it's giving 0 only. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 errors are there, but still it's giving only 0. So why it is happening? Just let's try to think logically. The moment you created this variable, no, error log lines, it's an integer variable. It's not a distributed variable. It's an integer variable, and probably it's residing in the driver's memory. And in the master node, if this code is getting executed. So this is available in the drivers or the master node's memory. And this particular for each function is being executed by all these workers. Your Spark program structure is this way. Like your entire program is divided into 2 types, driver program and worker programs. So when there is no such distinct files or distinct set of codes we create, but you think in this way, the statement where you are creating a Spark context object, or the statement where you are creating a RDD, okay, or so those are basically coming in there. Those are called as driver program, and you're applying transformation like map transformation, filter transformations, all these transformations and actions. These are executed by the worker nodes. Okay, so the driver basically understands the code, deciphers it, and identifies like how to break it into multiple tasks, create the execution plan, and then execute it on top of these worker machines. It doesn't do it by itself. Rather, it make it done by the executors of the worker machines. So this particular variable in the driver program, but this action is being executed with the worker programs. They have their own copies. Okay, they have their own copies. They just keep on incrementing that. Suppose first machine find out 2 errors, so it just incremented to 2. Second machine got it 3, so it just incremented it to 3, like that. Everybody has different copies. But when you are printing it, you are printing the same driver programs variable. So that's why it's same 0. These machines are having different versions of that, but again, these are in bits and pieces. And basis the number of records available in each machine, so that variable got updated to that. But the driver has the same 0. So this kind of problem is solved through accumulators. Okay, you created a variable Spark context accumulator. You started with the value 0. Then inside for each function, you say that accumulator.add1. Okay, every time you find a error, accumulator.add one. So there only it will just keep on updating that accumulator. So this is called distributed counter or accumulator. Okay, so all these executors are seeing the same copy, same accumulator what you have created. Okay, like that. That is the concept of accumulator. Okay, you are implementing a distributed counter because of this, because you are working in a distributed environment. You have multiple computers. Okay, one computer is called driver or the master node. Other computers are workers, so they are having different heap memory, different JVMs. So if you are creating one variable in one JVM and you are accessing it in other JVMs, so that will create different copies of the same variable. So after the computation, you will not find the consolidated result. So for that, Spark has a concept called accumulator, and you can create an accumulator and keep on accumulating the actual values into that. And broadcast variable, in the other hand, is basically you have certain data to be distributed across all computers. You can say RDD is also is that only RDD is a distributed collection only, but here it's different. So what I'm trying to say, so you are having some lookup data. Okay, you have a transaction or sales data and having sales ID or transaction ID, customer ID, product ID, amount, and all this. And you want to basically replace the product ID with product description or product name. So you have a lookup data. Okay, you have a lookup data called say basically product ID of a product name, and you want to replace that. So in that case, you can create a RDD and you can join them. But you know, my product data is only a handful of records, maybe 100 or 200 records. So in that case, creating RDD doesn't make any sense. Rather, I will create a list or dictionary, and I will basically make that dictionary available locally in each machines. So in that case, this operation becomes much faster. Your RDD is a distributed RDD. Sales data is a RDD that's distributed across multiple nodes of the cluster. But the lookup data is a certain type of variable or certain type of data type that's available on each and every machine locally. Okay, so when you are looking up the product name via or through that product ID, so it will be really fast because that other data set is available locally in the same machine's RAM. For every computer, it has a distinct copy. So operation become much faster. So that is solved through broadcast variable. Given a very small example, broadcast of 2, you're broadcasting an integer 2. And this map function, you're basically extracting that value and keep on incrementing this number. You have RDD of 1, 2, 3, and you want to increment it to say 2 each. So basically 3, 5, 3, 4, 5, that you can do it through broadcast variable. But yeah, you can basically take that as an assignment. So you have sales data having sales, having transaction ID, customer ID, and transaction amount, and you have a product data that is having product ID and product name. Now in the sales data, replace the product ID with product name through this broadcast variable. Getting my point? So sales data having transaction ID, product ID, amount. Okay, and you have product table, product ID. The product is a broadcast variable. Okay, it's a dictionary having key value pairs. Okay, product ID and name. Now replace product ID in sales RDD with product name from product broadcast variable. Okay, let's solve this problem. Okay, so that's all about your RDD part. Okay, we covered all this part which is required for the conceptual understanding as well as interviews. Okay, now then we can go ahead with this. Now then we can go ahead with this. What do you call this? We can go ahead with the Python part. Okay, next session. Any queries till now?
Siddharth, this is Sanjog. So can you go to the accumulator part once?
Yeah.
We can like do count, use count function and calculate the
Correct. You can do
number,
count.
right?
Yeah.
So what is the use of accumulator then?
Actually, we don't use accumulator as we have discussed earlier. No RDD, no accumulator, no broadcast variable, everything through RDDs, everything through data frames. But still, it's conceptual, it's there.
Okay.
In Hadoop MapReduce framework, that was accumulators, broadcast variable, those concepts were there. So those has been replicated here in RDDs also. That's why it's there. Otherwise, we never use these things in projects.
Okay.
But still, I can think of some examples, but I don't want to confuse you. But there are in projects, what happens sometimes we do, apart from the actual project work, we do some housekeeping activities. For example, so if you have heard about data lineage, not about Spark job execution lineage. So lineage is I'm not sure I should discuss it or not. But yeah, just think in this way, like lineage is a concept we do follow in every data pipeline projects. Lineage is what? So how your data travels from one format to another format. You read your source data, and that source data just you capture it or persist it into the staging layer. Then you read the data from the staging layer, do some data cleansing. Then you read the cleansed data, do some data analytics on that. So basically do some data curation and prepare intermediate data. Then further apply some transformations and write the data to the target data mart. So your data flows from one stage to another stage. Like means in your data pipeline, you have multiple hubs. It's not like you are directly reading the data from the source tables and populate the target data. It undergoes multiple layers. Okay, we never add a single point of failure. Think like your pipeline is running for 6 hours and it's just source to target. If your code fails, like the same 6 hours again you have to take. You have to run the entire application to produce the output. So that's why we intentionally add multiple hub. Okay, source to staging, staging is a location. Staging to cleansed layer, it's again another set of folders you're creating in your data lake. Then data lake, then staging layer to intermediate layer to target data mart. So all these hubs we add for failover mechanism. If it fails at one point, you don't have to recompute everything. Rather, from the previous step to the final step, you have to rerun. That's the only thing. So there it becomes super important to maintain the lineage. Okay, maintain the lineage. I mean, how many records you received and how many, what are the different matrices for the data. You calculate at each hub to basically keep a track, like, are you losing any records in any of this layer? It can happen, right? That maybe because of data issue, because of code issue, it can happen anything. You write a wrong join. Okay, some data has some missing records. You applied inner join. Okay, so you'll definitely miss the records for the non-matching records. You got some sales data, you got some customers data, but there is a lag between the in the source. There is a lag. Okay, so first sales data get updated and then customer data. If by mistake some sales data didn't come, like maybe that's customer table just fail, but sales data is still populated with the data. So what customer data is having few missing customers, but in the pipeline you applied some inner join and you proceed further. So what happened? So you completely drop those records, transactions records for which there is no matching record in the customer's table. And this is bad, right? This is wrong. You just made your data pipeline in an inconsistent state. So that's why basically lineage mapping is super important. Any production ready applications, we do keep track of lineage. Okay, how data moves from one step to another step. How many records were there in the previous stage? How many records in the next stage? Is there any data drop? Yeah, in some case, data will be dropped and business is already aware. So they will say if there is missing product ID, you have to drop those records, or you have to take those records and write it into exclusion folder. So later our platform team, they will analyze what went wrong with those records. But that should be a proof. That should be you should log these informations. Okay, this is called like lineage, data lineage. So in those cases, we can't write additional code for that. Okay, in a business logic, we don't add those logics. Rather, we implement these accumulators. Okay, so we do keep counting the number of records in the accumulators, and these accumulators get written to different directories. Means bigger companies, they have different systems altogether for lineage. So you have to update those accumulators in their file systems. Saying point A, you have 10 data sets. Each data set has having these many records. Point B, the same 10 data set transformed to another 10 data sets having this many records. Okay, and then point B to point C. So 10 data set merged to 7 data sets. These are the count of records. You do populate these numbers and they create different reports on that. Okay, means I do have those reports, but I can't share it because it's a client data. But they create different visuals. They have separate visualization team. They have created a report so that every day the support team, they can check the month, they can monitor the trend, how many records are coming and how many records are getting dropped. All these informations you can see visually. General support people are basically asked to monitor the reports at a daily basis. Is it there is a spike, a lot of records are getting dropped and all. So they should keep an eye. So by looking at those plots and reports, you can track like how the data flow happens from source till the target data mark. Okay, so instead of like writing extra code for that, we do embed these accumulators in our code to capture the numbers and then send it to a alert and monitoring system. Okay, alert and monitoring system is part of every bigger enterprises. So they will need your data every time you create a data pipeline. You have to comply with the existing systems. Okay, you need to send those matrices. You can implement that using these accumulators. Okay, so that's basically an example of real-time and real-time use of accumulators. Okay, so that's all for today. Okay.